we have seen that in probability theory, we have seen different types of functions that play a very significant role. Now, we know that random variable also can be treated as a function defined on a probability space from a probability space to the real line. So, the question is, does this constitute a very general class of, or can we define a general class of functions that will be useful or that can be applied or that can be used in many ways in probability theory? So, that is the basic question. And remember that whenever we are going to define a function, there is always a probability space on which we have to consider these functions. So, how to define such a function, or rather such a general class of functions, or whether we can give different definitions, and we can show that although we can define it in a number of ways, but basically these definitions are equivalent. So, in this spirit we are actually going to define, or we are going to study a general class of functions which are known as measurable functions. And it will be seen immediately that random variable is nothing but a measurable function. We will try to explore some of the properties of these measurable functions, whether we can define it with respect to a general set or a particular type of interval or different types of intervals, and we will try to explore whether one can go from one definition to the other. That means, if we define a measurable function with respect to one particular interval, or which can be applied on a particular type of interval, can we move from that type of interval to another type of interval or another type of set? And these functions actually will play a very important role in the integration theory, which we will discuss later. So, today we are going to study a general class of functions which are known as measurable functions. Obviously, that should be defined on a particular probability space. Measurable functions. We have already the notion of a probability space, or in general a measure space. That is, we have a sample space or a big set which is omega, and a script f which is a sigma field generated by the class of subsets of omega, and a measure defined on this omega and script f. So, if we consider a particular set, it can be easily seen that not every set is measurable. So, naturally it is important to know that which sets are measurable, or rather which sets occur very naturally in many situations in probability theory or in construction of certain types of functions, but these functions should be what is known as measurable functions. So, this measurable, this word measurable comes very frequently and very naturally in the context of any probability space, or when we deal with any probability of anything or distribution functions, this concept of measurability comes very naturally. So, we are going to explore this concept in more detail. Suppose f is a real valued function defined on a bounded interval, then naturally we can think of the Riemann integral of f in that interval. Probability theory sometimes requires much general integration process. Now, this generality in the sense that this should be applied to functions from an arbitrary set to extended real numbers. That means, a function may be defined functions that gives us an arbitrary values within an arbitrary set, or that gives us a value which is on the extended real line, or rather the function might be defined on a particular on a class of sets. But the condition, the important condition is that some measurability conditions should be satisfied in order to define or develop integration with respect to such functions. Another important thing is that probability considerations, or in the probability theory, we have encountered many times a particular type of measurable functions which are known as random variables, because we already know that random variables are nothing but functions defined on a probability space to the real line. So, this concept of measurable function comes very naturally and occur very frequently in the context of probability theory. In fact, since probability space, that is sigma, that is omega script f and p, is nothing but a particular type of measure space, it is a finite measure. So, we can also define this measurable function with respect to any general measure space. So, let us consider a probability space for the time being, which is omega script f and p, and let us consider f, which is a function defined on omega, or rather on this space omega script f to the real line, or rather extended real line. Now, corresponding to any event, or rather any point omega that belongs to big omega, we can compute the number f of w, because remember this f of w belongs to the extended real line. So, for every outcome of an experiment, we can define, that means for every event, or rather every point small omega that belongs to capital omega, we can always compute a number. We sometimes we need to compute a number which is nothing but given by f of omega. Suppose we are interested in the probability that f omega less than a f omega lies in the interval a to b, that is a less than equals to f omega less than equals to b. That means, basically we wish to compute that all probability of occurrence of all such omegas, or rather any one of these omegas, such that f of omega belongs to a, where a is nothing but the interval a to b. Now, this a can be any general set. Here as an example, I have given this a to b interval, but this a can be any general set. So, suppose we want to compute this probability of omega such that f omega belongs to a. Now, for this to be possible, that means let us consider the set omega such that f omega belongs to w, and this set is nothing but f inverse of a. Now, that means this f inverse of a, we can think of the probability of such omega such that f omega belongs to a, that means this set, only when this set belongs to the sigma field script f. Otherwise, we could not think of the calculating the probability of that event. That means, we cannot think of probability of calculating any event which does not belong to this sigma field script f. So, from here it is clear that at least for such a set that belongs to script f, that means we can calculate the probability. That means, this set f inverse a has some concrete feature or concreteness within itself. That is why, that means it can be measured at least in terms of probability, or we can think of probability based on this set f inverse of a. So, just extending this notion or putting this notion in a mathematical way, we can immediately say that if f inverse of a belongs to script f for each interval a capital A, then we say f is a measurable function. That means, f actually measures something. This gives us the measure of this set, and since f is a function, it is called a measurable function. So, let us consider capital X and script f be a measurable space, and except to r bar f star by f. So, this is a mapping from x f to r bar f star, mapping defined by small f. This is an let us consider that f to be an extended real valued function defined over x and script f. So, let us consider the formal definition, which is an extended real valued function f on x, that means it is defined on x, is said to be measurable if for each number a the set x such that f x less than a belongs to script f. That means, this set is a member of script f, and hence we can think of calculating the probability, or rather we can think of considering the probability measured for a set that belongs to script f. That is why we call f is a measurable with respect to the measure. In this case, we consider the measure as a probability. One can think of a very general measure are considering any general measure space, which in this case x f. So, thus this gives us the formal definition of a measurable function. Now, note that as we have already mentioned that we have encountered the concept of random variable many times during this discussion, during these classes on probability theory. So, and we have seen that this random variable is nothing but a measurable function. So, actually an almost surely finite measurable function on a probability space is called a random variable. So, when we discuss the random variable, we usually consider the probability space is the measure space of our interest, and any finite, almost surely finite measurable function defined on that space is called a random variable. So, now this actually gives a very formal definition, very concrete mathematical definition of a random variable which is defined on a probability space and which is nothing but a measurable function. So, this is a theorem. As I have already mentioned in the introduction that we can define this measurable function or the measurability with respect to many types of intervals. So, natural question is whether one statement implies the other or the other way around. So, to this page we are just putting down several statements, and this theorem ensures that these statements are equivalent. So, first statement is f is measurable, that is according to our definition x such that f x less than a belongs to script f for each real number a. So, we have considered this as a definition. Now, we are making another statement that x such that f x less than equals to a belongs to script f. Now, remember here we did not put the equality sign in the definition. Now, we are considering this set x such that f x less than equals to a. C f x greater than a belongs to script f, or set of x such that f x greater than equals to a belongs to script f, or x such that f x lies between a to b and this set belongs to script f for each real number a and b, a must be less than b. Now, these a to e, these statements are all made with respect to a particular type of interval on the real line. Now, natural question is, can we extend this to a general open set or general closed set, or in general, more generally for any Borel set? The answer is yes. We can define this thing for, suppose we define a G as an open set of R, then if inverse of capital G belongs to script f, and the same thing holds for a closed set f of R, that is small f inverse capital F belongs to script f, and consider the probably the most general situation, consider any Borel set E of R, then we can see that f inverse E belongs to script f. So, these are our claims, and if we can show that any one of the statements from B to H can be obtained from A, and because A we have considered so called the definition of measurable function, then we are through actually. So, let us try to prove whether A, the actual definition, implies any one of the statements, say H. So, first consider a class of sets D, which is E such that f inverse of E belongs to script f. E is any Borel set of the real line. First, we will prove that D is a sigma algebra of subsets of R. That means, if EI belongs to D, then f inverse EI belongs to script f, and we have to prove at least two properties. One is this D is closed under countable union and D is closed under complementation. So, we are going to prove this one by one. So, let us consider the first union, countable union situation. So, consider since EI is a Borel set on R, consider a sequence of Borel sets that belongs to D, that means EI belongs to D for every I equals to 1, 2 and so on. So, we can define the countable union of EI, that is union of EI I equals to 1 to infinity, and take f inverse of that set. Now, this is equals to union of I equals to 1 to infinity f inverse EI. It can be shown very easily, and this belongs to script f, because script f is already a sigma algebra that is known to us. Script f, since it is a sigma algebra, so it is closed under countable union, and since F inverse of countable union of E I is nothing but union, countable union of F inverse E I, and since for each I, F inverse E I belongs to script f, so it is closed under countable union because it is a sigma algebra. So, union of F I inverse E I, and hence F inverse union of E I belongs to script f. That means, this D is closed under countable union, or rather F inverse of union of I equals to 1 to infinity E I, F inverse of countable union of E I's belongs to script D. Now, consider again another set E, which is a Borel set, and it belongs to D, then F inverse E belongs to script f. That is quite natural, that comes from the definition of E, and hence F inverse of E complement equals to nothing but complement of F inverse E. Again, since script f is a sigma algebra, it is closed under complementation. So, F inverse of E complement of that quantity belongs to script f, and hence F inverse of E C, E complement belongs to script f. And since F inverse of E complement belongs to script f, naturally this belongs to, from the definition of D, this is we are considering, that means all such sets E complement such that F inverse E complement belongs to script f. Hence, D is a, already we have shown this for countable union, and now this is proved for complementation. So, capital D is a sigma algebra. Now, consider x such that f x less than a, that means F inverse of minus infinity to a that belongs to script f implies, since this belongs to script f, that means this will imply from the definition of D, minus infinity to a belongs to D for every real a. So, naturally, since F inverse of minus infinity to a belongs to script f implies minus infinity to a belongs to D, that means D contains Borel sigma field of R, which is script f. Hence, F inverse E naturally belongs to script f for every Borel sets E of R. Hence, we have proved the H part from the A statement. Similarly, we can show from any statement we can move to another statement or the vice versa. So, these statements are equivalent. The proof goes exactly similarly. Now, let us consider another theorem. So, C is a constant, f and g are measurable functions, then the functions f plus c, cf, f plus g, f minus g, f g, f by g, assuming obviously this is well defined, they are also measurable. Also, if f n is a sequence of measurable functions, then supremum of f n, infimum of f n, lim sup of f n, limit of f n, they are all measurable functions. And if limit of f n is a measurable function, if limit of f n exists, it is also a measurable function. The proof is very simple. Consider x such that f x plus c less than equals to a, which means x such that f x less than a minus c, that belongs to script f, because f is a measurable function. This is basic definition of measurable function. Then clearly m x equals to f x plus c is a measurable function. Hence, similarly, just by writing the whole thing, we can immediately write that lim sup of f n, we can write this as infimum of n greater than equals to 1 supremum over n greater than equals to n f n f m x. This is the definition of lim sup. Similarly, we can define lim inf, and they are also all measurable functions. Naturally, if limit f n x exists, this limit is exactly equals to lim sup, which is exactly equals to lim inf, and hence this is also measurable. So, all other proofs follow exactly similarly. Now, we will just introduce one small definition, which is known as complete measure, that is, a measure mu is said to be complete if subsets of sets of mu measure are measurable. Now, consider one small theorem. F is a measurable function and f equals to g almost surely, then g is measurable if mu is a complete measure. The proof is again very simple. Let us consider E to be the set on which f x not equals to g x, such that naturally mu equals to 0, because f equals to g is almost everywhere. Now, we can easily write x such that g x greater than a equals to x such that f x greater than a union x such that x belongs to E, g x greater than a minus x belongs to E, g x less than equals to a. Now, since f is measurable, we have already assumed that f is measurable, then the set x such that f x greater than a is measurable. Now, x belongs to E, g x greater than a is a subset of E, and x belongs to E, g x less than equals to a is also a subset of E, and mu E is mu E equals to 0. This implies that all these sets are measurable, and therefore, naturally x such that g x greater than a is also measurable, and hence g is a measurable function. I will just end this talk with a simple definition. It goes like this: an extended real variable function phi on x script f mu is called simple if it is script f measurable and assumes only a finite number of values, say alpha 1, alpha 2, alpha n. There is phi x we can write as summation I goes to 1 to n alpha I, indicator function of a I, indicator function over the set I of x, where a i's are disjoint measurable sets with union of a I equals to x. So, now we will see that this simple function has immense importance in the subsequent theory, especially in relation to integration theory. In this class, we have learned a particular general class of functions defined on a probability space, which are measurable functions. We have introduced the definitions of measurable function, some of its properties, and most importantly some operations that we can do with the measurable functions. As for example, we have seen that if there are two measurable functions, say f and g, the question is, natural question will arise that whether f plus g or f into g is also measurable. So, that means some operations within the class of measurable functions, whether they will lead to another measurable functions. We have also seen that the limit of a sequence of such measurable functions is also measurable. So, this actually broadens this area to encompass a large class of functions. In other words, we can encompass different types of random variables, because we have seen that the random variables are nothing but measurable functions. So, we can define sequence of random variables which are nothing but a sequence of measurable functions, and the limit to which it converges is also measurable, we have already seen. Another interesting observation, or rather concept that we have introduced, that means any measurable function can be written in terms of a very simple type of function, which is in fact known as simple function. This representation has immense importance in defining the integration in this area, in this probability theory, which we will discuss later.